All right, we're going to start chapter 2. Reminder that there's a quiz on Moodle that has to be done this week, and finish up. If you haven't, you have a little time to finish up the Moodle quiz from chapter 1. So chapter 2 is an introduction to chemistry that we need for biology. It's not true chemistry, but chemistry we need for biology. So the kind of things we need to know are to be able to discuss the features of atoms, to describe how electrons behave, and why atoms form chemical bonds and molecules. And then, really, we're going to talk about water. That's kind of where we're headed. So, um, let's go to the next slide. What is chemistry? Chemistry is the study of matter, solids, liquids, gases, anything. Everything is made by small particles combining together to form these things. Chemistry is a physical science, very important on its own, very important for biology. So that why do most people not like chemistry? Well, it's pretty abstract. Um, it's something that lots of people are afraid of. There's lots of math and equations, and then of course, if you've had chemistry, it's a lot of word problems, and so most people are not all that keen on chemists, and that includes most biologists. We're all scientists, but often biology is very different from chemistry. And even though sometimes chemists study biological molecules, often it's from chemists kind of come at it from a different way, and they're more likely to be much more focused on math and ratios of things. So chemists and biologists often work together, but there's some differences. So anyway, it's kind of my jokes. So uh, the basic unit of all matter, solids, liquids, and gases are atoms. Okay, atoms are the smallest particles that contain all the properties of the matter. They're something that we can't get any simpler by chemical means. And all atoms consist of several basic subatomic particles. Here's an illustration from your text showing a simple atom that's helium. Helium has 2 protons, 2 neutrons, and 2 electrons. And all atoms are made out of protons, neutrons, and electrons. What makes an atom of a particular type is the number of protons. So this is helium. All helium atoms have 2 protons. Okay, helium can come in several different forms. That means it may have different numbers of neutrons. It may have different numbers of electrons, but if it's got 2 protons, it's helium. Okay, so there are something like 92 naturally occurring elements, and then there are some elements that have been made in the lab. This shows the periodic table of elements, again from your textbook, and they're arranged in a very specific way to show their chemical properties, and they're shown in groups. Okay, the simplest atoms having the fewest protons are up in the top. And so H is the chemical symbol for hydrogen that has only 1 proton. And so it's the first one. And then way over on the other side of the top is helium. Helium has 2 protons. And so the atomic number is the kind of shows you the position, how high in the chart it is, and that's the number of protons. Then in each box here, there's a chemical symbol, different symbol for each element. And its name is there, and its average mass is there, which is the number of protons plus the number of neutrons generally. So which atom has 6 protons? Well, we'd look at the periodic table of elements, and we'd see, over here, there's carbon. It has the chemical symbol C, and that 6 stands for 6 protons, and so that's how we know. And so I won't, you don't have to memorize the chemical table of elements, periodic table. You don't have to memorize the symbols. we'll be talking primarily about 5 or 6: hydrogen, carbon, nitrogen, oxygen, just a few of those. But I want you to see this. Um, and so another thing about atoms is atoms of a particular type sometimes come in different forms. One form are isotopes. And isotopes all have the same number of protons but different number of neutrons. Okay, and so here are 3 carbon isotopes: um, carbon 12, carbon 13, and carbon 14. And these different uh, isotopes have somewhat different properties. They're all carbon, they all form the same types of chemical bonds, but some isotopes are very stable, like carbon 12. Others are unstable, like carbon 13. Carbon 13 is unstable, and after a while, it may give off a particle where it actually can revert to carbon 12, or not carbon 12, to nitrogen, and so that is a kind of unique feature of it. One application of these different isotopes is that these unstable isotopes, they convert to a different form at a steady rate. This is called the half rate or half-life, and this decay allows us to measure the different forms of carbon, and that tells us how long that chemical was made. So when they ever talk about carbon dating is looking at the number of isotope molecules present. The other kind of different forms of atoms are referred to as ions. And sometimes it's more stable for an atom to give up or pick up an electron. So it will have different numbers of electrons and it will be charged. And so like here, this upper guy here on the left, that's a sodium atom, which has just 1 electron in its outermost shell. That's kind of unstable, and so it tends to want to get rid of that electron, so it has a 0 in that outer shell, and then the inner shell is full. On the right side is chlorine, and chlorine has 7 electrons in its outer shell and strongly wants to pick up another so that outer shell is full. And so sodium and chlorine are actually more stable as sodium and chloride ions. And so sodium gives up an electron, which has a negative charge, so the sodium ion has a positive charge, and then chlorine picks up an electron, becoming a chloride ion, and so it has an extra electron, so an extra negative charge. Okay, and so this is part of what causes things to form chemical bonds, is to get the right number of outer electrons. These are sometimes called valence electrons, and to get these stable arrangements is really important. In ionic bonds, like sodium chloride, the resulting charged atoms tend to stick together, and so that forms an ionic bond, which is shown on the right there. In other cases, we form covalent bonds where atoms share electrons. Like here, these 2 hydrogen atoms sharing electrons to form a hydrogen molecule. This sharing is called covalent bonding, and it can be a very equal sharing, in which case we call it non-polar covalent, or it can be an unequal sharing, where the electrons spend more time near one side, and so they will become partially negative and partially charged positive. And we can share more than 1 pair of electrons. We can sometimes share 2 pair, and so that's called a double bond. Okay, and so this sharing of electrons doesn't result in any charge, but the electrons, or the atoms, at least partially have filled orbitals, and many biological molecules have these covalent bonds. And so here's kind of a picture of these things. And so these electrons are spending time near both the center of both atoms. And so this is a pretty stable arrangement. I'm going fast here. It's okay. You can slow down and repeat it. Just play it over again. Okay. So the last thing I want to do today is talk about water. Water is formed by 2 hydrogen atoms forming polar covalent bonds with an oxygen atom. And so oxygen is sharing electrons with 2 hydrogen atoms. And so this results in an oxygen that has a partial negative and then hydrogens that have partial positive regions. And this is allows these partial negative regions to be attracted to partial positive regions of other water molecules, and this is called hydrogen bonding. And this is why water has some unique properties. It's why it remains a liquid at such a wide range of temperature. It takes a lot to separate it, so it can store heat quite well. Water is also good at dissolving a wide variety of things because it can dissolve ionic compounds and other polar covalent compounds. And water molecules want to stick together, so they have surface tension. So here's just a picture showing these hydrogen bonds again from your textbook. Okay, and this is why water has these unusual properties. And again, water is cohesive. The hydrogen bonds means that individual molecules are attracted to other molecules. It's a weak effect, but it has a large cumulative effect. Okay, and this is important for life because living organisms like us are mostly water. We use water as our transport medium. We use water to dissolve things. Water is important for chemical reactions. It has these features, okay, and so these special features are what make life possible, and so I'm listing them here. And the search for water is really, really important. We just had a bunch of space missions the last couple years to Mars. And the question, is there life on Mars? What would it look like? Well, all living organisms have water, and so a lot of this search is really about the search for water. And so here's a bunch of different ideas on Martians. But the key thing is, before we ever find Martians, we need to find water. And so that's what we're doing. And missions to the moon now are looking for water because people need water. And if we look for in the right places, we're likely to find water. So the search for life is the search for water. And minerals that form in water can tell us maybe water was here before, maybe there could have been life there. And so not only are we looking for water on Mars and the moon, but we're looking on the moons of Saturn, which are Titan and Enceladus. And if we find those things, we will hopefully find living organisms. So a big important application. So let's stop there. Remember, there's a Moodle PowerPoint, or a PowerPoint, and quizzes to look at. All right, good.